little lecture, lab for the routing technologies, routing protocols. This is lesson 11, module 11. I like to put the routing protocols more in the front end than on the last day when it's like, okay, let's see if we can get finished and get gone, because these are a big deal. These are the things, the labs, and I keep saying labs. You really got to do the labs. You can't pass, although some people say you can. I don't think you can pass a Cisco test if you can't do the labs. You can kind of mess it up, but if you can't do it at all, I don't think you're going to be successful with those certifications. And the routing protocols obviously are a big part of that. So with that, we'll go into two different types of classifications of routing protocols: distance vector and link state. And the distance vector protocol that we talk about is RIP. Distance vector advertises its routing tables to its directly connected neighbors. So it tells, and sometimes this is called routing by rumor. Let me get my pen going here so I can scratch or try to get my. I may have overloaded the machine to the point that nothing else is going to run. Oh, there it is. Good. What it does. Now I got to just find the pen that goes with it. There it is. What it does, if we have routers in here, and we'll have big network numbers, network 1, 2, 3, 4, they're connected. We enable RIP in the routing protocol. Router A tells router B, I know how to get to network 1. So router B adds network 1, and it's already got 2 because it's directly connected. And in the beginning, all a router knows about it are the things that are directly connected to it. And once it gets the network A to B, A advertises network 1 to B, B puts it in its routing table and says, I got to go to router A to get there, and adds 1 to the hop count. And that goes on down the line. B gives it to C, and it puts network 1 in, and it now becomes a hop count of 2 to get to network 1. And then C advertises it to D. In RIP, every 30 seconds it does an update. So it takes a little while to get these things into convergence. So A tells B, and then B tells everybody it's directly connected. B tells A and C about it, and then C tells D on down the line. So a distance vector protocol advertises its routing table to all directly connected neighbors. Frequently at regular intervals, lots of broadcast. And it is a broadcast protocol. Not a big deal, because broadcast protocol from A to B, B is going to stop the broadcast. It'll go to all of the networks that are available. But it'll broadcast these things every 30 seconds. When it becomes available, all routers need to be updated. And RIP has the capability to say, okay, the route's down. It's called a poison. So it's going to poison the route, and the way it poisons it makes a hop count of 16, which is infinity in RIP. It can't only go 15 hops. So when we talk about distance vector, and the distance vector protocol that we have is RIP, it is used on small networks if we're using dynamic routing protocol. Each router will have to advertise the new information to its neighbors, which will make it longer for the routers to accurately determine a view of the network. And what that's saying is that, every 30 seconds. So route 1 goes down, A tells B, okay, route 1's down, we'll poison it. B tells C, and then C tells D on down the line, until everybody says, okay, that route is no good. I can't get to network 1 anymore. They use fixed link subnet masks, which means that we're going to use class full network addresses on these things. Cannot be scaled, can't be subnetted. RIP's an example. And this down here in blue, distance vector routing protocols which work by having each node share its routing table with its neighbors. In the link state protocol, the only information passed between the nodes is connectivity related. Link state algorithms, and I've got another one for it, are sometimes characterized informally as each router telling the world about its neighbors when we look at these things. So distance vectors share it with their neighbors. Link state, and to kind of use the title, they say it's the state of the link. So link state protocol will make its routing decisions based on the state of the links that connect the source and destination. And maybe the Wikipedia down here, the basic concept of link state routing, and then we'll look at the rest of the bullets, is that every node constructs a map of the connectivity to the network. So it constructs a map, and from it, in the form of a graph showing the nodes are connected to each other, each node will then independently calculate the best logical path. So they get the network topology, the entire topology, and then from it, and based on the state of the links, and each is going to use its own measure of cost to get there, will find the best path through the network. But back to the bullets here, the state of the link describe the interface and its relationship to the networking devices. Interface information will include details such as IP address of the interface, network mask, type of connected network, and the routers connected to the network. The IP address implies, and we can subnet these things. They are classless networking routable. These are routing protocols. Routable protocols, the one that we use, IP. Routing protocols, RIP for small networks, OSPF and EIGRP would be the preferred, and that's what this one is about, is OSPF and EIGRP for both IPv4 and IPv6. The information will be multicast, not broadcast. So another big deal here, multicast using various types of link state advertisements. So it's going to use a 224.5, but it's going to use a 224 address, and the hosts that it's going to go to, the nodes it's going to go to, are all of those that are running that particular routing protocol. So if we put OSPF on a router, it becomes a member of the OSPF multicast groups, and multicast uses groups. You have to be a member of the group in order to get that information. Store a collection of the LSEs in the link state database. Include LSAs for the links of the router. Will be subject to the Dijkstra algorithm, and mathematical formula will extract the data and create the routing table based on the information that comes in. So it's going to create the routing table. The Dijkstra algorithm extracts the data. It's going to create its own topology of the network. It'll have a topology table, and from that it's going to create the routing table. There may be multiple paths to get from one point to the other, and what the algorithm does, extracts the data, determines the best path. OSPF opens shortest path first, then IS to IS, and IS to IS is not an objective of the CCNA, and it is one that in all the courses they always say, oh, it's there, but I've never configured IS to IS. OSPF, if we have a mixed network like Joel's saying he's working with, OSPF is going to be the preferred protocol. If we have a completely Cisco network, EIGRP, the hybrid protocol is going to be the one that would be preferred. RIP, small network, chatty, class full, we can't do any subnetting with it. And then after we have these two types, we have interior routing protocols and exterior routing protocols. Interior routing protocols under a common network administration. That's what you and I are going to use on our networks. Will be interior routing protocols, interior gateway routing protocols. You may hear them called referred to as interior gateway protocols. Need to specify all the routing protocols with a list of associated networks before the routing activities can begin. What does that mean? To specify with all of the associated networks. If we have a router here and a router here and they're connected together, and we have maybe a couple of networks on it, VLANs for instance, and a couple of networks on here. When we go in and specify the routing protocol, and in OSPF would be like router OSPF, and then we have to specify a number that associated with that particular instance of OSPF. We have to then tell the routing protocol to advertise the networks that are attached. That activates them for that particular routing protocol. And that includes the network that goes from the router or router to router. What we do when we put the network for the connecting interface and it activates it on it, and it activates it on that interface and allows it to advertise off of the network. So the routing process will listen to updates from other routers on the associated networks and then advertise its own routing information to the same network. So the process winds up being similar, same on the machines themselves. The interior routing protocol supported by Cisco on-demand routing protocol, RIP, IGRP, and I think that if you've got some really old routers, IGRP may be there. It's an old Cisco proprietary routing protocol that doesn't appear on the new routers. OSPF and EIGRP, which is an enhanced version of IGRP, and then the intermediate system, the IS to IS protocol, are the routing protocols that are available on these systems. Exterior gateway routing protocols. Exterior, when you see these things, think internet, and BGP, Border Gateway Protocol, is really the only exterior routing protocol used today. It's used to exchange information between networks that do not share a common administration. But again, think internet. We're talking about big organizations sharing their route tables so that we can get into those ISPs, get to individual resources in those ISPs. Also referred to as exterior gateway. The following information is required before the routing can begin: a list of neighbor or peer routers with which you need to exchange the routing information, a list of networks that need to be advertised as directly reachable. I know how to get to these networks. And then the local router's autonomous system number. We're going to have a couple of autonomous system numbers. EIGRP is going to have those. BGP has an autonomous system numbers. They're the same but different. The autonomous system number is like an ISP would have an autonomous system number, and these are assigned, and then they share their information based on those numbers. In EIGRP, we give it an autonomous system number, and all of the routers that use the same autonomous system number talk to each other and share routing information. If you have two autonomous system numbers, we have to force them to share that information with each other. Hybrid routing protocols have characteristics of both link state and distance vector protocol. Link state metrics but at the same time emphasize more accurate metrics than the conventional distance vector. Also converge more rapidly than distance vector protocols. Don't incur the overheads of the link state updates, but they do not incur those. Balanced hybrids are driven by events, so they only update when there are changes. The event driven, periodic, and thereby help conserve bandwidth for the real applications. Open balanced is almost exclusively associated with the Cisco EIGRP protocol. EIGRP, I've read some articles that say, yep, Cisco's made it available to other vendors, but other vendors aren't using it. I guess they're afraid that at some point they'll say, hey, yeah, okay, now that you got it installed, it's proprietary. But generally, you're only going to find it on Cisco routers. And I said, if you're in an all Cisco environment, it's the one you want to use. The advantage here is when we have failures. OSPF had the topology. It had a topology table, and it listed, kept track of, mapped the topology. EIGRP maps the topology, and it also maps backup paths, which OSPF doesn't have. If OSPF has an issue, it has to go and reconstruct the topology. EIGRP can simply go to the backup topology. It's kind of like, and all of these things are kind of like if you're using Google Maps to get from one place to the other, get to work, and you know that you have bottlenecks at times, and you look at the traffic and an overview. You've got your primary path, and then you've got alternates. So GPSs usually give you a couple of different ways to get from one location to the other. I think mine gives 3. So EIGRP would have the primary path, the recommended path, as well as some backups. OSPF would have the primary path, the recommended path, and then if anything happens, it goes and determines a new recommended path based on any of the changes that would happen there. EIGRP, the best aspects of distance vector and link state that none of the performance limitations and penalties of the two protocols are incurred. And Jeremy Charon, and if you've ever seen some of his courses, he's very entertaining, said it's the best protocol that has ever been developed. IGRP, and they've got this slide in here, so we'll talk about IGRP. It is developed in the mid-'80s. It's no longer on their routers. It was used for routing multiple protocols, and this is the key here, multiple protocols. This is when we used multiple protocols, IP, IPX, DECnet, AppleTalk. It could route all of those protocols. Some of the newer protocols are IP focused because that's what we're using. The internet runs on IP, and so does everybody else at this point in time. Support a hop count of 100 and advertise every 90 seconds. Remember, RIP was a hop count of 15 was the max, and it advertised every 30 seconds. Advertise less frequently, use less bandwidth than RIP. Converged slower because it took 90 seconds for IGRP routers to become aware of changes, just like we talked about with RIP was every 30 seconds, which is a slow converging. 30 seconds is an eternity in a network, as all of you who have worked on them and do work on them know. If the internet goes down for 5 seconds, you're probably going to hear about it. But 90 seconds, think about that. 90 seconds, a minute and a half, and how big is your network? 100 hops, it's going to take a long time for this thing to get into convergence. OSPF, open shortest path first, which we've heard the term a little bit earlier, is a true link state protocol developed as an open standard for routing IP across large multi-vendor networks. Multi-vendor here being some of the key words, which means that if we have Cisco and whoever else, and Joel's got a bunch of these, I think, OSPF is going to be the protocol that you have to use if you're going to use a link state protocol. Provides support for IP subnetting, tagging of externally derived routing information, permits packet authentication, so we can use authentication so that we don't have somebody put a rogue router in our network. IP multicast when sending and receiving packets, multicast, not broadcast, so that it sends it to specified machines, specified routers, and these are going to be the routers. The multicast group is going to be those routers that have OSPF installed on it. Sends link state advertisements to all the connected neighbors of the same area, and it's designed for much larger networks. We have areas which are similar to autonomous systems, similar to any grouping. We group these things together. The first rule, I guess, that is the first OSPF network or OSPF area has to be area 0, and it's going to be classified, called, labeled the backbone area. Then we can connect other areas to it, inter area OSPF, which means we would have a router in here with one interface in area 1 and one interface in area 2, and then they can share the information. Area 0, routers share information with the routers in area 0, area 1 share information in area 1, and then we have an area border router here that has sticks its toes into both areas, and it gets the routes and sends them across the borders for them. When we started to send hello packets to all the directly connected OSPF routers, contain information such as route timers, router ID, and the subnet mask. If the routers agree on the information in the hello packets, they will become OSPF neighbors. After they become neighbors, it'll establish adjacencies by exchanging link state databases. So they're going to exchange the databases, and then we'll use the Dijkstra algorithm to create the route table we want. The router will. Some smart guys figure that out. Routers on a point-to-point, point-to-multipoint links will automatically establish adjacencies with interfaces as a broadcast and Ethernet or non-broadcast multi-access frame relay. We'll use a designated router that establishes these adjacencies. So if we're in an Ethernet environment, we're going to have a designated router. We're also going to have a backup designated router. And what these things do is all of our router buddies here will send their updates to the designated router instead of sending them to the world. The designated router will then update the other routers. Backup designated router is there. If the designated goes down, the backup takes over, and then you elect a new backup. And these things are elected based upon the highest IP address on a loopback interface. And if you don't have any loopback interfaces, it's the highest IP address on the routers themselves, any IP address. But the loopback is the preferred method, and that's where we talked about in ICND1 making loopback interfaces. They are used here. The I guess issue would be if we did just the IP address of the interfaces, they may change. The loopback interface we can leave there and not change it. You can also use the loopback interface, loopback IP, for management. So OSPF commands, we're getting ready to get into the lab here. Like I said, tonight is a little bit of lecture and a lot of lab, but continuing with routing, the next topic, and this is kind of just, I think, stuck in there. We talk about routing protocols. You did an OSPF lab, and then we're going to talk about OSPF again, version 2 and version 3. And then we stick inter-VLAN routing in here. And inter-VLAN routing in ICND1, we did the router on a stick. So what this says is a feature that enables you to route traffic between different VLANs. It's required when the end station wants to communicate with another end station on a different VLAN. We know that. Within a VLAN, we'll be able to communicate with another one without the help of a router or some type of routing device. Uh, Devices in different VLANs will not be able to communicate with one another without a router. I don't know how many times you can say that on a single slide. What we're talking about here, and we have this router here in a couple of interfaces, yeah, that works great as long as you only have a couple of VLANs. You have 10 or 15 VLANs, we're not going to probably put 10 or 15 interfaces on an individual router to get there. So what we did, ICND1 was a router on a stick. What we do in ICND2 is called switch virtual interfaces. We use a layer 3 switch here, and on these just show that yeah, we can and can't communicate. The red VLAN is the 192.168.3.2, so I should be able to ping 192.168.3. What's that one over there? 4 on a different switch, which tells me that I have a trunk through here. And then if I try to ping the 2.2, that shouldn't happen, and it doesn't happen. So I have trunk port here. We've kind of shown that there is a trunk port between this switch and the layer 3 switch, and we can go to the layer 3 switch and show interface trunk that in fact it is. Status is trunking, the VLAN is 1, encapsulation is 802.1q. If I show run, this is in Packet Tracer if you use it. This is when we did the trunk. When I did the trunk on it, I had to specify the encapsulation protocol, because since it's a layer 3 capable device, there are other encapsulation protocols that are available on it. So it's not routing. What we're going to do is go into it and create virtual interfaces. So yeah, first of all, let me go back and show VLAN. What I did here and what I said I like to do is VLAN 2 is the .2 VLAN, and then 3 is the .3 VLAN, so that it makes it easier for me to keep things straight. And on this one, I don't have any ports in any of these VLANs. They have to exist here so that we can send traffic, and it participates in the VLAN, in the trunking. So we can go into config T and do interface VLAN 2, change state to up, so we have it, and we'll give it an IP address, if I can spell address, of 192.168.2.1, and we have to specify the subnet mask 255.255.255.0, and it says it is changed state to up, so it already ought to be up. We'll see here in a minute. So next we need interface VLAN 3, interface VLAN 3, and we'll make its IP address 192.168.3.1, 255.255.255.0. So now, with any luck, if I go back to this guy, I hopefully can ping 2.2. Waiting. This is always a lot of fun. So it works. Switched virtual interfaces. Layer 3 switch. We just go in and create the virtual interfaces. We also have to have the VLANs on it. They don't have to have any ports on it, but they have to be there in order for that to work. And get rid of that. Get rid of some of this stuff. So the switch virtual interface allows it to represent the VLAN as one interface to the routing and the bridging and switching. These bullets, yeah, we'll go through them, represent the VLAN switch ports as an interface to the routing or bridging function of the system to associate only one SVI with a VLAN. So one switch virtual interface with a VLAN, yes. So we have to make a virtual interface for each of the VLANs that we want to communicate with each other. If we had 5, we could do that. The advantage here is they are virtual interfaces, so we don't have to go in and have physical interfaces for them, and we can get there using the trunk ports. Can provide connectivity only to the system will be created the first time you enter the VLAN interface configuration command. You saw that in the demo. Correspond to the VLAN will correspond to the VLAN tag associated with the data frames. VLAN 2 is going to be associated with the VLAN 2 tag frames, obviously, and the IP subnet. And this is again the one that, for me, I'm a pretty simple-minded person. To keep it straight, I like to do VLAN 2, the .2 network, and on down the line like that. This is just an image of what I did with the demo. Routing issues, speed mismatch. The router and switch may both use the speed interface subcommand to set the speed if we want to do that. And these are things that they're probably going to be okay unless we do something to modify the defaults. Auto config, we shouldn't really have an issue with the speed or duplex mismatch on these things. The interface could be shut down. It says in the neighboring switch port, it uses port security, could be an air disable mode, or no or bad cable, or the wrong cable if it's not a device that supports the auto MDI, MDIX. Troubleshooting VLAN routing issues, the same things that we have done over and over again. Ping, if we're not able to ping between the devices on the same VLAN, we need to be sure that they actually are on the same VLAN. Verify that the source and destination ports are on the same VLAN. If we're not able to ping on the same VLAN but not on the same switch, be sure it's a trunk port between them. I could do that because I had a trunk. The ones on the same switch were, in fact, the ports were in the same VLAN. Let's see, test ping is successful in step 3. But if this step fails, initiate a ping from an end device connected to the switch to its corresponding VLAN interface. Is unable to reach the end device, you need to verify that the default gateway of the connected device is correct. Yes, that the default gateways are correct. I've done this before and forgotten to actually add the VLANs to the layer 3 switch. Then they don't participate in the trunking, then the information doesn't get there. So default gateways, all the things that you've heard about over all of the courses, how to troubleshoot these things. What can we ping, what can't we ping? And then trace route, wherever the trace route fails, that's generally where the problem is going to be. If we're unable to reach the internet or corporate network, need to verify that the default route points to the correct IP address. Usually we only have one way out of our corporate network, and so we can use a default route to get it there. That is the end of the SVIs, and the next thing is OSPF, or routing for IPv4. Sends hello packets to the OSPF enabled interfaces to discover the other OSPF routers, and after a neighbor's discovered, the routers compare the information in the hello packet to see if it's the same information. If it is, it's an okay, and we will establish an adjacency. Adjacency, and this is a note that I have, it says not all the neighbors will be able to establish an adjacency. Some neighbors will become fully adjacent based on the network type, and the designated router establishment will share LSAs, link state announcements, with their neighbors, while other neighbors will not be able to do so. Adjacency will be established using database description packets, link state packets, and link state update packets in OSPF. Let me bring a not real complex OSPF configuration over here. And I think these all have OSPF running, and we have from loading to full, so we have adjacencies. When we look at these things, show IP OSPF, and then we can show our neighbors. And this one says full adjacency DR, the designated router. Full, and the designated router we only need in the Ethernet connection, and in this one we have one Ethernet connection and 2 serials. So the 2 serials show up as full, but we don't need a DR for them. And the neighbor ID, the ID is the highest IP address on these things. And if you look at these things, they will be the highest IP address, 192.168.10.1 up here, and 20.1. Let's see if those are it. Yeah, 10.1 and 20.1, and the other one down here, 103.1. I don't have the addresses on it, but it would be, there we go, loop, because it's got some loopbacks on it. 103.1 is the highest loopback address, so that's going to be the router ID on these things. And while we're here, let's just look at some other things. I can see some stuff. If I just show IP OSPF, it tells me about the protocol, the routing process, and the process ID on these things we have to assign. It is only significant locally. It allows the router to keep track of that particular OSPF instance, which means that we could have a couple of OSPF instances running on it. Scheduled delay 5 seconds, hold time between short SPF, shortest path first transmissions is 10 seconds. Link state intervals are 5 seconds. So you can see this thing really kind of works relatively, I don't know, quickly, I guess. It's going to come in, converge relatively quickly because of the way it does. But remember, it is not a broadcast. It is a multicast sort of arrangement. Let's just show IP question mark. We can look at the database, which gives us some information. Doesn't give you and me, I think, or at least me, a whole lot of stuff, but it shows that there's information there. The topology table you can see in a router. It's not available in Packet Tracer. Do the question mark. We did neighbors, or do interface. This tells us which interfaces OSPF is running on and which areas it's in. When you do the configuration, you have to have a process ID. I'm losing my mind, as well as an area number on those. And this one is broadcast, and this one down here is point to point. So it knows what type of network it's on for those. And no backup designated router on this network. It doesn't need a designated router. If we go up here on the broadcast network, the designated router is 192.168.103.1, and the backup is 172.16.10.5. It's there. We have the hello time, the dead time, how long it's going to wait before it declares that particular route dead. And if I do show IP route on these things, directly connected here, I got an OSPF route here. 110 is the administrative distance and 65 is going to be the cost. What I have on this one to go to the 10.0 network, which is, that's the 20 up here. 10.0 network, from here I have one serial link, and these default to T1, so it's going to be T1 speed. And the reason is, I'm going to show you a table in a minute of what the costs are, and this doesn't have multiple possibilities But if we had multiple possibilities, the shortest path, the cost, is the thing that it's going to do. So we're going to have a cost here, and this is going to be a fast Ethernet. So we have one serial, one T1, and one fast Ethernet in the cost of this thing. So sends hello packets after it's discovered, compare information, whether the routers have compatible configurations. It will try to establish an adjacency, which means that the routers are going to synchronize their link state databases to ensure that they have identical OSPF2 information. Share the link state advertisements of these things, and then they'll flood these LSAs out to every OSPF enabled interface so that the routers eventually have a link state database. Once that happens, then we go into the reduced bandwidth updating of this thing. When they have the identical, they're going to be in convergence. This is the cost table, and if we hear the T1 is cost of 64, and then a fast Ethernet and faster 100 meg or higher is 1, which gives us a 65, and that was the cost of that link. So it uses cost to find the best path for these things. So area, we do have to specify an area on these. An area is a logical division of routers that links within the OSPF domain, allows you to create separate subdomains within it. A single area is where all of them are within the same OSPF area. Be able to limit the CPU and memory requirements required by routers by dividing the OSPF into areas. If we have a relatively large network, we may need multiple areas because of the amount of resource that this takes. It's something that should run on most routers depending on how big the network is, and that's something that has to be, you have to look at the specifics of the routers themselves. The flooding is within an area. They don't flood out of area. And we assign an area ID to the interfaces within the defined area. And the area ID, the 32-bit value, it uses the highest IP address. IPv6 or OSPF v6, OSPF v3, OSPF for IPv6 uses an ID that is similar to this. So this one is a single area. Multi-area, we kind of talked about. We talk within the areas, and then we have an area border router that has an interface in each area, and it transfers the information from one area to another, to more than one area. Then one or more will become an area border router. Will allow us to connect the backbone areas together, have a separate link database for each area that it connects, and it defines one other router type, an autonomous system border router, which goes to another administrative area. And you can think about this, if you're going out of yours into maybe an ISP's would be an autonomous system border router to another autonomous system. And autonomous systems are those that are managed by another individual. And then there's a series of labs, but there's a few, and I've added some stuff in here, but 2 or 3 slides for IPv6, OSPF IPv6. I'd like to go ahead and do that and just then have lab time for the rest of the night. But it is one that is available, OSPF for IPv6 version 3 protocol supports some additional features, provides support for IPv6 routing prefixes and IPv6 addresses, the larger ones. The LSAs need to be expressed as a prefix and a prefix length. When we do configurations, you use the /, the prefix /64 or whatever the length of the network address is instead of the subnet mask for these things, or actually a wildcard. The router ID and the area ID are a 32-bit number with no relationship to the IPv6 address. So we do have to configure the router ID for this thing. So it uses the link local, and this is for neighbor discovery. These things use the link local IPv6 address for discovering the neighbors. We also use it as the default gateway if you're using static routes for these things. We can use IPv6 authentication, and then it redefines the types of LSAs. And I've got a slide here in a minute of the link state announcements that are available in each of these. The first step is to create an OSPF v3 instance, assign a unique instance tag to it, and we'll have to configure additional parameters. The router ID has to be configured, administrative distance, log adjacency changes, maximum paths, and reference bandwidth are things that may or may not. The multi-area adjacencies, primary interface to more than one area, and if we only have a single area, it needs to be area 0. I'm going to go look at a couple of configurations here in a minute. Adjacencies, multi-area establish a point-to-point unnumbered link in the OSPF area and provide a topological path for that area. Multi-area exists as a logical construct over an existing primary interface for OSPF. A lot of fancy words for we're going to have something that has an interface in each of the areas. And then the multi-area establish neighbor relationships with the corresponding interface of the neighboring router, and then it will be allowed to send information across it. These are the LSA types. Type 1 is generated by each router for each area it's located in. Type 2 is generated by the DR, the designated router. The link state ID is going to be the router ID of the DR, and again, the router ID is the highest loopback address. Unless there is no loopback address, and then it will be the highest IP address that's on the device. Type 3 is a summary. It's created by the area border routers and flooded into other areas. OSPF likes to do summarization of routes, so you need to construct your networks in such a manner that they can be summarized or supernetted. And it just says that, you know, if we had like a 10.60, 255, 255, 10.60s, whatever, subnetted as class C's, it says send all the 10.60s to me, and then it will send them on to the other ones. Autonomous system border router, type 4, the summaries, type 5, external link, autonomous system, external LSAs from another autonomous system, type 6, and it's there, multicast, but it's not supported. Type 7 are external, known as not so stubby. And we have stub routes, stubby routes, not so stubby. There's a lot of definitions, and these are in here, but stub routes and stubby and not stubby are not part of CCNA. This is a table that you can look at that who generates the LSA and what does it accomplish, and then the type 1, every router. Routers advertise their connected interfaces, and again, back to what we said earlier, initially what a router knows about is what's connected to it. It tells everybody else what's connected to it, that you can get to this network by going to me. Type 2, designated routers on non-point-to-point links, because if we have point-to-point links, serial links, we don't need designated routers. They're only going to be in the Ethernet routers. Collects the type 1 LSAs and sends out a single type 2 representing all of the routers on the link. This is used to build the shortest path tree on these things. The type 3 area border routers, single LSA representing all the type 1 and type 2 LSAs in an area, reduces the number of LSAs on the routers. Type 4 area border routers connecting to an area where there are external routes. And then type 5 routers with a redistribute command. And what redistribute allows us to do is to put other routing protocols into an OSPF. And for instance, if we had a bunch of EIGRP routes, we could then have those routes on a router, and OSPF routes on a router, and we could redistribute EIGRP. We would go into the OSPF and use a redistribute EIGRP command, and then it would accept the EIGRP routes, put a cost on them, and then advertise them to the other OSPF routers, so that we wouldn't have to have the same routing protocol running on all of the routers. And then type 7 routers with the redistribute command that are in the NSSA is not so stubby area for those. And again, the functionality and feature table here, protocols, the OSPF multicast address 224.0.0.5. They kind of did us a favor here because they end with a .5. FF02 OSPF3 FF02 tells us that it is an IPv6 multicast address, and then the DR and BDR multicast 224.0.0.6 FF06. Multiple instances per interface, no and yes, and then authentication, plain text and MD5 authentication for OSPF version 2 and IPv6 authentication. Unicast routing is enabled by default. IPv6 unicast routing is not enabled by default on Cisco routers. You have to, in the config, give an IPv6 unicast routing command in order to activate IPv6 routing. Header sizes 24 bytes, 16 bytes. LSAs, the number 7 and 9, and the interface IDs, the IPv4 address for OSPF, and then the link local address for OSPF v3. Interfaces per link, 1 for OSPF v2 and multiple for version 3. This is just a Wireshark capture of some of this stuff that you can see these things, the attached routers. We have the link stack type, network LSA, the information that's in it, an open OSPF packet. This is just there to show you what kind of information goes on these things. I just threw this in to show you. Yep, there is a big calculation that goes on to find out the OSPF version 3 calculation. The version 2 is basically the link cost that we had in that other slide. But this is what would go on in the OSPF v3 calculation. Then there are those what I wanted to do, and I guess what we actually maybe could do is to go in here and maybe slide in another router, 2620 here, and what interface am I on? Fast 800.0.0, and see if I can make a fool out of myself. Which one was that? 00? 0, 0. So let's go in here. Interface passing to 0/0, give an IP address of 192.168. I don't know what I haven't used. Must use 200.1, 255.255.255.0. Do a no shut. And let's try IP OSPF, and then we need a process ID, and again a process ID is only locally significant. Okay, and then area, area 0 in this thing. So we have to specify process ID and an area, and then we're going to give our network commands, I think. Let's see, LM. I don't need any of that. Oh, I'm on the, never mind, I'm on the interface. Let's try this again. So we'll do router OSPF, and then we'll do the process ID, and then the carriage return. Cannot start, there must be at least one up interface. I guess I didn't do that, huh? Interface fast 0/0. No shut. Do show IP interface. Brief, and let's see, it is up now. Excellent. So now let's try router OSPF 1, and then we'll do network 192.168.2.0, and then we need a wildcard bits. The wildcard bits, when we do this, 0 says I don't care any, no, it actually 0 says check it. So it says check to see if it's 192.0 to check to see if it's 168.0 to check to see if it's 2.255. I don't care. This could be anything. So we will allow anything in the host IP address. And then after this, we have to tell it what area that interface is in, and we'll use area 0. And then let's see. Times 192.168.200.1. So we have this thing going here, and it's not going to work, is it? Because I got to be able to communicate with something. These should be on the 1010 network, and I'll put my other network down here. The hazards of doing it on the fly. Oh. And I don't have another interface. I can show you the configurations here, and this one's up and running. Show run. Actually, let me stop here and stop the recording